Welcome to our lesson on the Hertzsprung-Russell diagram, also known as the HR diagram. This is one of the most important tools in stellar astronomy, helping us understand the life cycle and properties of stars. But what exactly is the HR diagram? It's a special graph that plots stars according to two main properties: their luminosity, or how bright they are, and their surface temperature, or how hot they are. When astronomers plot thousands of stars on this diagram, interesting patterns emerge that reveal the life cycles and different types of stars in our universe. Let's start by understanding the axis of the HR diagram. The vertical axis, or y-axis, represents the luminosity of stars, how much energy they emit. This is usually shown as either absolute magnitude or in units of the sun's luminosity. The higher up on the diagram, the brighter the star is. The horizontal axis, or x-axis, represents the surface temperature of stars in Kelvin, or sometimes their spectral type or color. Importantly, temperature decreases from left to right, which is the opposite of what you might expect. On the left side, we have hot blue stars. On the right side, we have cool red stars. Astronomers often use spectral classification instead of temperature on the x-axis. Stars are classified as O, B, A, F, G, K, or M types based on their spectral properties. Astronomy students often remember this sequence using the mnemonic, "Oh, be a fine girl / guy, kiss me." O-type stars are the hottest with temperatures above 30,000 Kelvin, while M-type stars are the coolest with temperatures around 3,000 Kelvin. Our sun is a G-type star with a temperature of about 5,800 Kelvin. Now let's plot some stars on our diagram and see what patterns emerge. When thousands of stars are plotted, most of them fall along this diagonal band called the main sequence, which runs from the upper left to the lower right. Stars on the main sequence, including our sun, are in the stable phase of their lives, fusing hydrogen into helium in their cores. Our sun is here, in the middle of the main sequence. In the upper right region, we find stars that are cool, but very bright. These are giants and supergiants, stars that have expanded to enormous sizes. Red giants, like Betelgeuse, have diameters hundreds of times that of our sun. In the lower left, we find white dwarfs. These stars are hot, but dim because they're very small, about the size of Earth. They represent the final stage for stars like our sun after they've shed their outer layers. The HR diagram also reveals information about star sizes. Stars of the same radius form diagonal lines across the diagram. The stars in the upper right are giants and supergiants, with radii hundreds or thousands of times larger than the sun. Stars in the main sequence have intermediate sizes. And stars in the lower left, the white dwarfs, are very small, about the size of Earth. Let's show some actual scale comparisons to understand this better. The HR diagram isn't just a static classification tool. It also shows us how stars evolve over time. Stars like our sun start their lives on the main sequence, fusing hydrogen into helium. When they exhaust their hydrogen fuel, they expand and cool, moving up and to the right on the diagram to become red giants. Finally, they shed their outer layers, and the remaining core becomes a hot but dim white dwarf, moving to the lower left of the diagram. More massive stars follow a different path. They start as hot, bright O or B-type stars at the top of the main sequence, evolve into supergiants, and end their lives in spectacular supernova explosions, potentially leaving behind neutron stars or black holes. Now that we understand the HR diagram, let's see how astronomers use it in practice. Here's a cluster of stars plotted on the HR diagram. By analyzing where stars are on the diagram, astronomers can determine the age of star clusters. Younger clusters have more massive stars still on the main sequence, while in older clusters these stars have already evolved. The distance to stars, by comparing apparent brightness with the intrinsic brightness we expect from the HR diagram. Physical properties like mass, radius, and internal structure. Let's summarize what we've learned about the Hertzsprung-Russell diagram. It plots stars based on their luminosity and temperature, revealing important patterns in stellar properties and evolution. The main regions are the main sequence, where stars spend most of their lives, giants and supergiants in the upper right, and white dwarfs in the lower left. The diagram shows us not just what stars are like, but how they change over time, following different evolutionary paths based on their mass. It's one of the most important tools in astronomy, helping us understand the life cycles of stars and the structure of stellar populations throughout the universe. The Hertzsprung-Russell diagram stands as one of astronomy's most powerful visual tools. By plotting just two properties, temperature and luminosity, it reveals the incredible diversity of stars and the universal patterns in their evolution. Next time you look up at the night sky, remember that each of those twinkling points of light has its own place on the HR diagram, telling a story of stellar birth, life, and eventual transformation. Thank you for exploring the Hertzsprung-Russell diagram with us today.